to take a look at what kind of operations can you perform on your functions. We can subtract them, we can add them, we can multiply, we can divide them. We're still going to look at your domain and your range because the only time it's going to change is when we divide them, because the only thing that ever gives us a problem is the denominator. So we're going to take a look at domains and ranges at the same time. And I gave you these notes as well so that it would be a little bit easier for us to walk through them. Basically, you're saying just this. F plus g at x, we're saying, okay, take the f function, add it to the g function. Taking the difference, subtract the f function minus the g function. Now, you have to be careful on this minus. If it's more than one term, you have to put parentheses around it, and we'll take a look at that. Product just says you're going to have to multiply them. A quotient says we're going to divide them. It's really very basic, and that's all we're going to do with them at this point. So let's take a look at, let me make sure I'm clicking here. Let's take a look at an example here, and it'll make a little bit more sense. We have two functions, the f function and the g function. We're going to perform a sum on these two functions. So we're going to say, take f of x and add to it g of x. And we should come out with one function, one rule, that combines the two of them. So we take this piece, and we take this piece, and we just add them together. We combine like terms. We've got an x squared. A 2x and a 2x is a 4x. And the negative ones cancel out. God bless you. Thank you. The negative ones cancel out. So this is our result for f plus g at x. We're just coming out with one more function. Do we do anything with it? No, not really. We just kind of add them, subtract them, multiply them, and so forth. Now we can evaluate them. We can evaluate the sum when x is 2. It helps us from when, remember we did the steps with the compositions? If you do f of g of x, you have to do the g, then you have to roll it into the x. So if we put a number in here, you took 2 steps. If we did it in one equation, you just put it in that equation. So this time around, when we evaluate it, we're evaluating this when x is 2. We don't have to do it to this one, do it to this one, and then add them together. We have one common rule. So we say 2 squared plus 4 times 2. This gives us 4 plus 8. This gives us 12. The long way, we would have had to do it twice. We would have had to put the 2 in here. 2 times 2 plus 1 gives you 5. 2 squared plus 2 times 2 minus 1. This would give us 4 plus 4 is 8, minus 1 is 7. Then we add them together, and we would get 12. So we're creating one rule to be able to take the sum. It's kind of like your composition of functions. Create one rule, and then you don't have to keep doing them in 2 steps. To subtract in this case, you would have to be really careful on your subtract, because what's going to happen is you're going to take the f function, you're going to subtract the entire thing for the g. This is the one that gets a little bit tricky. And a lot of you fall into this mistake. You can't subtract the first term. You've got to subtract all of them. So you're going to be negating not the first piece, but everything that follows. And then you're going to combine your like terms. So on a subtract, be careful of what you're subtracting. You're going to have to distribute that negative sign if it's more than one term. The one that gives us a little bit of trouble is the division. So the first thing we're going to do is take a look at these domains. And then we're going to see if it changes when we divide. So our domain restriction for a radical says it cannot be negative. So we're going to set x greater than or equal to 0. So here's my number line. Good so far? Now, we're going to come down here, and we're going to do the same thing. But this has a quadratic. So the quadratic says, factor this, set them equal to 0, and on your number line, this one, you got it? I didn't know which one you meant. So here's my -2, here's my +2. So I'm allowed to use these, but I have to test. This parabola goes like this. And I want my positive, I'm going to put my positive in a different color here. I want my positive right in here. Right? We're combining a lot of things here. But I have to make this so that both of these domains will work. So I can't use this little piece right here. I can use from 0 to 2. So my whole domain is 0 to 2. Because this piece uses from here on out, this piece only uses this little section. So where do they overlap? Right there. There's my domain. Follow me on this one? Okay, we have two different functions. But we're going to be combining them in the same type of function. So we have to look at both of their domain restrictions. So we have to be able to take a value and put it into either one. So now I can use 0. I can put a 0 in here. I can put a 0 in here. I can use 1, 1.5, 2, 1.999. I can put a 2 in both of these and have this work. I cannot use 3 because 3 will not make this work. So my domain right now is from 0 to 2. When we divide, we go like this. Take the F over the G. And unless it can be reduced, you can leave it like that. You don't have to rationalize anything. The nice part about precalc is we don't have to rationalize denominators. We can leave them like that. So now what we do is we just take a look at the denominator. What will cause our domain to change when a radical is in a denominator? Let's go back to here. This is the one I'm on here, -2 to +2. They were both closed because they could be equal to 0. But now they're in a denominator. What changes? They can't be equal to 0. So now I got to take this guy and I got to take the 0 out of here and out of here. So since this was where my domain is, my new domain, because of this divide, says you can go from 0 to 2, but you can't use 2. The division is the hardest one. We'll always have to find domains of our functions, but when you divide, you somehow change the domain a little bit. How come half of you guys write, half of you don't? Yes.
So would you always go through that first process that you did?
Yep. Yep. Always find a domain first. We didn't in the other one because our domain was all real numbers in this one. So I didn't go through that one. I should have mentioned it though. Now, what happens if I divide the opposite way? Here's my number line up here. So I was at the 2, at the 0, and at the +2. And my domain was right in here before. But now, which will cause that to make my domain change. What's going to change now? My domain went from 0 to 2. Let's go back to your original domain. With radical, the square root of radical x in my denominator can't be negative, and it also can't be what else now in the denominator? 0. So now I have to lighten up this guy. Can't be 0. So now, for this one, here's my domain. My domain changes slightly on a divide. It doesn't change on an add, it doesn't change on a subtract, and it doesn't change on a multiply. It just changes on a divide. Okay, now we're going to look at finding the domain of a composite function, which we actually just did. We're going to do this again. We're going to find a common domain here. So, I've got one function, which is what? When I graph this, what do I get? Parabola. What's its domain? All real numbers. So far, not so bad. No restrictions. Now I have a radical. And what can this radical not be? It can be 0 this time, but it cannot be negative. So we take this out, and we set this greater than or equal to 0. Now, it's a quadratic. So it makes a parabola, right? Which way is it going to open? Down. So we know we've got a restriction in our domain somewhere. So now I know to factor this. Think these things out. Because otherwise you're going to stare at it and say, what do I do with that? Don't add 9 to the other side and take the square root. You will end up with the roots, but then you have to put that on your number line. So x is 3 and x is negative 3. Put these on your number line. And these can be closed. Now which way does your parabola open? Down. So here's the zeros of my parabola. And I want the positive. I want this in here. So my domain is from negative 3 to positive 3. This domain was all real numbers. So now I'm restricting it when I combine the two of these. If I'm going to use the two functions together, they have to share one domain. So to be able to use the two together, I'm going to have to share this domain. I can still work the equations, find the common equation, but my total domain has to be the one that they'll both be able to use. Because this one cannot use all real numbers. So now I can work this out. Take my g of x, take my f of x, take this whole thing and take this x out of there and replace it. This g is going into this f. So this is not as bad as it looks because even though this is a radical, this is a square. So we've got 9 minus x squared minus 9. And what happens when you square a radical? It goes 1. It comes out. 9 minus x squared minus 9. And we can take these guys out. And your resulting is negative x squared. We still have to use that domain though. We still have to keep that domain. It's a composite function, and just like we did on the other one, we have to keep the domain that both of them can use. This is the hardest part, the domains. But are we getting a little bit more comfortable with them? Starting to make sense, right? It does actually make sense. You have to step back and look at your work. That's when I was looking at some of you saying a horizontal move up or down. Think about what you wrote. Take a look at it. It does make sense when you read it. So make sure when you look at things, you say to yourself, oh, I have a parabola. Oh, it's going to go like this. I have a restriction in there. Okay? Think things out. Now, you can always work these backwards. If I end up with this, I want to find two functions that made this. Let's go this way. See if you can think of two functions that when I do f of g of x, I end up with that up there? Think. Give me two functions that when you put one into the other, you're going to come out like that. Normally, what are we replacing? We're replacing an x, right? So think of this as an x. Think of this one as saying 1 over x squared. I'm going to put this into this guy. What am I putting into that? X minus 2. So if I take x minus 2 and I plug it in for that x, don't I get that? See it? See it backwards? That's a good thinking question. Helps you think about it. And it depends which way I'm going. Which one is F, which one is G. Okay? And then one last thing. When we look at compositions of functions on a graph, okay? So we're going to start here. We're going to add these two together. This guy is my f function. This one is my g function. We're going to say when x is 0, what is the value of my f function when x is 0? Here's my x of 0. What is the value of my f function? 2. What is the value of my g function? -1. And what is 2 plus -1? 1. We're doing this on your graph now. Okay? When x is 1, find my f function. This is my f. Here's my 1. What's the value? In other words, what is the y? 3. Plus, when x is 1, what is the y of g? 0. And what does that become? 3. Okay, do the next two. See what you come out with. Same way. It's the same as we did before with 1f. Now we just put 2 graphs. We put a composition out there. For the first one, when x is 2, what's the value of my f function? 1. Everybody see that? When x is 2, there's the 1. When x is 2, what's the value of my g function? Yeah, like 0.5. We would have to estimate to be 0.5. Okay. When x is 3, what's the value of my f function? 2. And when x is 3, what's the value of my g function? 0. Okay. So you can do this? All right. That was not bad, right?